Let's do another example of using the first derivative test and critical values to help aid in graphing a function. So it says let r of x equal this, 3x minus 6 to the 2/3 power plus 2. Find the critical value to find intervals of increasing and decreasing and compare with the graph. So this is a little different question, but all very similar applications of this. So let's go ahead and just go ahead. Again, we want to start with the derivative because that is how we find our critical values. So derivative of this, again, I have something with 2 to the 2/3. I could use the power rule here because I have something to the 2/3. Or again, I could write this as a cube root squared. Another way this could be represented, but we can go ahead and drop the 2/3, leave the inside alone, and subtract 1 from 2/3, which would leave us with negative 1/3. Also, remember that since there's something other than just x on the inside, we need to apply the chain rule and multiply by the derivative of the inside as well. So the inside is 3x minus 6. Derivative of 3x minus 6 is just going to be 3. So can't forget to multiply by 3 to all that. And then derivative of 2 is just 0. So that second term will go away upon differentiation. Also, notice we'll have 2/3 times this times 3. So this 3 and that 3 will actually just cancel. And this will leave me with 2 times 3x minus 6 to the negative 1/3. And I'll go ahead and clean this up because a negative power, I could always flip that back under because negative power means division. But this would be 2 divided by the cube root of 3x minus 6. Because again, that would be 2 the 1/3 is the same as the cube root, and negative means divide instead of multiply. And this is probably the cleanest way of writing the first derivative of the function. So now, if we want to know where the critical values are, well, it would mean that we need to know when is this equal to 0? 2 divided by the cube root of 3x minus 6. And we need to solve such an equation. And this is a little bit of a different equation because it's not just a polynomial. But actually, something to remember about fractions is they can only be 0 when the top is 0. Because dividing by 0 is always something that's not possible. And this brings up another case for critical values that we haven't talked about yet, is how, so far we've looked at when is it equal to 0. But remember, critical values are where it's either equal to 0 or where the derivative is undefined. And notice that this function would be undefined when the denominator is equal to 0. So in essence, when either the top or bottom is 0, those would both correspond to critical values, even though the bottom would not be a solution to this equation. So technically, this has no solution. There is no way to solve this equation, but I could figure out critical values by looking for where it's undefined as well. So I'll just go ahead and erase that. Or instead of erasing it, I'll just say this has no solution. But there is a location where dividing by 0 is not defined. I guess I won't write this out, but I'll just set the denominator equal to 0 because this would be not an answer to the equation, but it would be a position that would make our derivative function undefined. So if I cube both sides, cubing 0 is 0, and then I could add 6 and divide by 3, but I could solve where is the 0 of the denominator. Or again, we can solve the undefined values by setting the denominator equal to 0, which would result in x is equal to negative 2. So again, this is not a solution to the equation, but this would be an undefined value, as we typically call it in algebra, or also corresponds to various behavior in the function. But essentially, this would still be a critical value. That's my point. So c is equal to 2. Let's just use c for our common notation for critical values. And again, not just from setting the equation equal to 0, but also if the equation was undefined ever also qualifies. And again, we could use the first derivative test to figure out, well, what's it look like? And if we want to know where it's increasing and decreasing, same deal, first derivative test. Hey, Ben. My dog is over here requesting attention. Give him a quick pat. There we go. All right, so we could, again, draw our little number line, place our critical value in the middle, and I want to check values to the right and to the left. So let's just say 1 and 3, and I want to check, again, plug it into the derivative. Oh, hey, we're begging for attention, are we? Yes, hello. A couple pats is not good enough. But we want to check the value in the derivative. I'm almost done. I'm almost done, buddy. Stop. I'm being attacked. But if we plug in 1 into the derivative or 3 into the derivative, what would that give us? Let's find out. I need my hand. Please, can I have my hand? Thank you. So if we plug 1 in, that would be 2 divided by 3 minus 6. So this would be cube root of negative 6. That's negative, so this would end up giving us a negative value. If we plug 3 into the derivative, that would give us 9 minus 6 positive. 2 divided by positive is going to be a positive. So basically we have a change from decreasing to increasing. This will be a local minimum value by the first derivative test. And anytime on the next exam, I guarantee you there will be a question where I ask you to use the first derivative test at some point in time. If you draw it with this sort of number line, that's exactly how. You don't have to do it exactly this way, but this is if you draw it out like this, it's a nice visualization tool for what's going on to determine it. But at the end of the day, again, if we wanted to know the intervals of increasing and decreasing, it would be determined by those. So we know it's going to be decreasing to the left of 2, and it's going to be increasing to the right of 2. And if we go ahead and type it in and check out what a graph of this function looks like, this is a fairly cool looking graph. If you've never seen what a 2/3 power looks like before, sort of looks like a double rainbow type of a deal. But notice that there is a critical value happening right there at x is equal to 2, as we figured out by looking at the derivative. And notice on the left-hand side, it's decreasing because it had a negative derivative, which is exactly what we figured out up here. And on the right-hand side, it's increasing because it had a positive derivative. And if we were to write those as intervals, it would be decreasing from negative infinity up until 2, and it'd be increasing from 2 up until infinity. Which, again, you can solve these by the graph, but other ways of using the first derivative test to help figure out what graphs look like, properties of increasing, decreasing, mins, max, all of that together at the same time.